Okay, so this is a brief approach of how logical AIDs could communicate with one another. So we have Alice and Bob here, and they cannot send message directly to their heads, so they use some devices to communicate on their behalf. Then they may have multiple devices, and then would need to synchronize state between devices of what happens in this conversation. And this is not always possible, since guys may not be online at the same time, and even if they are, they may be behind symmetric firewalls, symmetric NATs, where your address depends on the address of where you send messages. So it's like with hash linking of two objects that point to each other. Their content depends on the content of what they refer to, and here your address depends on the address of where you want to send messages to. So you can't have that. So for that we could use some mailbox, and personal mailbox could be used, but then it kind of breaks these devices communicate with one another. Now it's hard to achieve that. So we could use something like that, where each of the devices within some logical ID have mailboxes. And those are generic, but let's say for example, it will be DIDComm mailboxes. Simple ones. So for that, each device could use a distinct key from that they use to control this identifier. This is to protect from correlation from this second party intermediary, so it doesn't know who are the AIDs talking. So that gives us some metadata privacy with regard to this second party. For SPAC message format, TSP protocol, that would be a similar idea. So you use some different key that the one of logical identity is talking. So the message which contains ESSR message, which contains source and destination identifiers, those identifiers are not correlatable with actual identifiers that do the talk. That's why we could use it's an optional privacy metadata privacy protection feature. Without it, we could use still logical identifiers. This personal device identifier, and third party would not be able to learn that there is a relationship between these logical identifiers, but mailboxes intermediaries would see in signed plain text that this message coming from this AID to this AID. So to protect, we can use this optional privacy protection feature of creating some extra personal device outer AID, which will hide, which we can use for ESSR messages, but in that message we would have a nested payload from logical IDs. And if we take a look at how it works with DIDComm, on example, say we have Alice and Bob and Carol. So this is Alice's ID. She created personal identifier, and now she can create with Bob's ID, and Bob on this side can do the same. What's interesting here is that in this personal identifier, we see that it's controlled by a device, but this device set a distinct mailbox, which it uses here. So if we have a device of Bob1, Bob2, and they collaborate in jointly managing of this identifier, they would use their device mailboxes to talk to each other. So for any collaboration that these devices embark, they use this mailbox. They could use this mailbox as approach explored here. But for any outer communication, they use mailbox, which they set here with a different key. This allows to decorrelate communication in two scopes. So this is one scope. So this device, when it embarks in any communication, direct messages to some other identifier, and things like collaborating here with other Bob's devices, it uses one mailbox. And for any collaboration communication that this device embarks on behalf of this identifier, it uses distinct mailbox. And if we have Bob participate in some group, like a B group, device B1 would set another mailbox to further decorrelate any communication that happens on behalf of Bob and any communication that happens on behalf of this AB identifier. So when they connect, this is the information that's been exchanged to the other party, the ID to which you want to connect, and some representation of devices that communicate on behalf of this ID in form of keys. That's the approach explored here. So this connect invite includes information such as time has been created, some nonce, signature to be used. Well, it's demo, so it's not the target identifier in form of hash, but that would be set in real setup. And some information about init key. This is like a personal device AID alternative analog, and mailbox, which is to be used. So this can be seen, well, this is a human representation of the first key that device uses, sets here. That's the way it can be identified on. So it has shaded to it mailbox information. And also it comes with this init key and current signing key, which this device uses, and some target threshold. So whenever they connect, by exchanging out of band this information, the other party can use those mailboxes to contact this other party. And in this topic, which comes attached to the first event, describes what AIDs and what membership information it contains. So init key, did PS, those init key use current signing key of those init keys, ID keys. So now B1 sends novel key events that the other party does not yet know. In this case, it's all kel, which consists of one event. And ideally, at this point, other party would verify that the keys that this device uses correspond to the kel. So it would authenticate the other party. So that's the approach with DIDComm, to use separate mailboxes for each identity. This, however, does not decorrelate communication that happens within this within the conversations that B, say, embarks on. So any contact that B has, group which it is a part of, everywhere the guys will be using this mailbox in order to send messages to this device of B. And if there are multiple devices, they set their corresponding mailboxes that is used to contact them. And we see that, so that's one simple approach. I like it due to simplicity, but it does lack DDoS protection. I'm not sure how to do that with DIDComm. For that, we would need to somehow whitelist, so intermediaries can make drop decisions early. Presently, anyone who Bob contacted know Bob's endpoint where to send messages to and can DDoS Bob. So intermediary will not drop traffic, and those messages will come to Bob, and drop decision will happen at that end, which is way not efficient. SPAC paper goes into detail of DDoS protection, and like it says that so yeah, I've been saying it elsewhere, but at the bottom here in appendix is a bit of crucial information, which is DDoS protection, with which in mind I think the above protocol has been designed. So intermediaries, you come to your intermediaries and say that the other intermediaries are trusted. You whitelist some other endpoints, some other AIDs, and their IP addresses. So this intermediary can make efficient drop decision first based on IP address alone. So it's on the firmware layer, and drop decision that is cheap than at software load balancer level, where it may be up to 10 times less efficient, but this load balancer can look at the source identifier and perhaps destination identifier to make drop decision. So if source identifier is not whitelisted, it makes drop decision, and it looks at signature to verifies that signature as coming to from the source identifier. And if here malicious packet managed to slip through, which means that authorized whitelisted source identifier is the one who is doing DDoSing, and it turns out that the packet is somehow malicious at further software layer, which may be 10 times less efficient yet again. A decision can be made there, but if it's made there, then we have non-reputable proof that this source identifier doing some malicious work, so it can be dropped from whitelisting. So it is a fine, efficient scheme of DDoS protection, which I'm not sure how to apply to DIDComm. Alright, so that is the logical AID to logical AID communication, and how it can be done with DIDComm in a simple way, problems it has, and that we could use SPAC with ESSR messages and authorize our corresponding intermediaries. So in SPAC they will not send messages directly to each other, but they'll send it to their mailboxes, to their intermediaries, given they previously authorized established trust relationship between those intermediaries. So Alice would need to come to Bob, connect out of band with respect to this communication channel. They may use prior established communication channel if it exists. So they will need to perform this relationship formation between intermediaries, whitelisting each other's identifiers and IP addresses. So this intermediary now stocks up messages from this intermediary, and then it can pass message further on to the device, and vice versa. And this ESSR message, yeah, it contains it contains a source identifier and destination identifier. So intermediaries know, intermediaries know to ID token, and for that we can create this external identifier, which will appear in the message, in the plain text portion of the message. So intermediaries do not know the actual logical ANDs token. These ANDs, they only see this external identifier. That's the approach that SPAC message protocol format proposes under this triple nested protocol, which is listed somewhere here. Non-shared intermediaries, and goes into the interaction, saying that we can use interaction ID. So the recipient knows to which interaction this message belongs. It can look up the corresponding interaction in its database and add this message there. And we have this triple level nested protocol, which describes that both parties could exchange messages between this outer identifiers A3 and A3, which actually has a payload of okay, I think that's the identifiers, logical identifiers that do the talking, and we hide it in another message. And here are our outer AIDs that intermediaries can see, but they cannot see the nested payload. I think that's how it's described here. All right. So here is that.